Thank you, Kelsey, and good afternoon, everyone. I assume good afternoon in most cases. My name is Chris Gentle. As Kelsey said, I'm the Program Director for Information Management for WA Biodiversity and WA Marine Science Institutes. In Western Australia, both of those organisations are set up to effectively be a broker between industry, research and government in terms of getting after wicked problems in this particular instance. And our challenge right now has been working through, from an information management perspective, how we can de-risk as a community and regulation start to push us towards understanding cumulative impact of pressures on our environment, how we can use data and data science to help make that process more quantitative and less qualitative or less opinion-based as we work through the process. We've come up with a series of novel ways to broker some old challenges. We've got two key challenges in our mix, first of which is access to information. When a lot of it is collected by proponents, some of it is held commercially in confidence. How can we get access to the information to help to inform the appropriate degree of modelling and predictive tools, which is Matt's area of expertise, for how that particular process can then be interpreted by proponents, regulators and community in terms of helping to reach certainly a faster decision, hopefully a better decision, and ideally one that has a positive balance of environmental and ecosystem outcome, as opposed to just considering an economic type argument and outcome. Our program has been running for approximately 7 years. It's certainly scaled radically from where it started of one person to where it is today. And both Matt and Brendan will walk you through a case study that we've been developing up in Cockburn Sound. The Cockburn Sound project kicked off in earnest 4 years ago in terms of planning, and the results of what you'll see today is due to an awful lot of work by Brendan and his team in terms of the platform, the data engineering, and the visualizations of what's occurring, and a long period of history from engagement into understanding the science and the ecosystem side of things from Professor Matt Hipsey in terms of the modelling piece itself. My role, I'm a little bit of a fraud. My role is to coordinate and to make these two guys give them all the conditions they need to be successful. And in return, they're doing an awesome job of developing up products which are now in use by industry and about to be in use by our regulator. So I might stop there. Brendan, if I pass to yourself.
Thank you very much. So, Brendan Bush, I am the technical lead for the SEAF platform. It is my role to help coordinate and design and implement the underlying infrastructure that is the SEAF platform and what we go through today, as well as working with the various science teams in order to facilitate what their requirements are on the platform. So today we thought we'd break out the call more into a case study about what is occurring on SEAF. SEAF can be a little bit of an odd duck when we're talking an infrastructure platform, just on how it's designed, and hopefully we get across the point about why it's such an odd duck and why we've moved away from more traditional monolithic style platform deployments into what is architecturally known as a hub and spoke architectural model for the SEAF platform itself. And as we go through the Cockburn Sound story, we'll touch on various tech points as well as the scientific points that Matt will talk about. And so if you have any questions, if you want to delve more into the technical side of things, just chuck your questions in the chat and we can approach them as we come through. Or if you want to delve more into the science and how Cockburn Sound and the science platform Cesium that Matt's developed, then yeah, go for it. Cumulative impact. SEAF's primary role and the reason we were designed and the reason our design philosophy is such as it is we are tasked with trying to figure out how cumulative impact can actually be implemented in a real world situation. Cumulative impact, fairly easy to understand and historically impossible to actually implement. So from a regulator's point of view, how can a regulator assess the various different projects and developments that are occurring within a region or within an ecosystem so that they can assess each of those based on their cumulative impact of all groups' impact on that ecosystem? How can they do that in a sustainable, safe way whilst also maintaining security, data governance, data ownership, and all of the factors that sort of make a cumulative impact assessment a very difficult process. This has been ongoing for many, many years and well before my time with SEAF. So I joined roughly around that 2022 period, but Chris has been driving this initiative vastly much longer than sort of both mine and Matt's involvement. So SEAF. SEAF as a concept is a hub and spoke architectural model. And what we mean by that is that although SEAF has a central hub that governs basically the laws of the land within SEAF, so how people are onboarded, enter IDs, the RBAC designs, the sort of the infrastructure side of thing is all governed by the hub. That is what SEAF controls. However, for each region, you're going to need a different scientific solution and a different scientific program in order to start to tackle those cumulative impacts within that region. So something like Coburn Sound, which is a water body off the coast of Perth, is a vastly different scientific program and requires vastly different compute facilities than something like a groundwater study in the Pilbara, which is again vastly different than, say, a biodiversity study. They require different compute facilities, they require different storage, they require different scientific groups to come on board. How we manage that infrastructure. So we've designed this hub and spoke so that we have the flexibility to actually implement different programs on the same platform with the same governing rules, but provide different infrastructure for the different groups. When we talk more down the track, and as Matt goes through the Coburn Sound philosophy, we'll get to a bit of the sort of internal design of SEAF. So SEAF has a multi-zonal architectural model. In order to bring on different organisations, different competing organisations, and an example of those might be, say, a BHP and a Rio Tinto working on the same platform for a shared goal, we designed the multi-zonal architectural model with Microsoft in order to allow both a secure, isolated environment for each to work in, as well as then different zones, as we call them, different infrastructure on the platform in order to perform tasks where both sets of data or both sets of models are coming into. And I'll expand on that more as we go through the Coburn Sound case study. But I'm going to throw it over to Matt, who will go through Coburn Sound and give you a picture of the complexity of that ecosystem, and then we can start to talk more on how we've designed that infrastructure.
Great, thanks, Brendan. Yep, so I want to, a picture is 1,000 words, and particularly with the SEAF platform, it's really a couple of things. It is a software architecture and a software IT platform, but it is also a design philosophy of how groups work together, how modeling and data can be undertaken for various different use cases and so on. And the best way to really present the benefits and the power of SEAF is through sort of taking a bit of a deep dive into a case study. So I want to take you through one where we've been motivated to sort of build this technology, and that's in Coburn Sound off the coast of Perth in Western Australia. And really the motivation here, as Chris said, is there's competing uses, and we're forced to sort of tackle this challenge of cumulative assessment. And there's been a long history of environmental decline and also environmental management. There's been historical use, where we've lost a lot of ecosystem values, but there's also a lot of success where environmental policy has kicked in and led to some sort of recovery of the system. There's a long history that we won't go into today, but just so you understand, there's a lot of industry that has been active in the region, and there's also a lot of investment going forward. In fact, there's about $30 billion worth of future investment on the table over the next 10 to 20 years, and that really has both the federal and the state government regulators sort of motivated to how can we make sure we get the best, not just for industry, but also for the environment. And so this is really the backdrop for why we're sort of developing this system. And just to give you sort of an example of what this looks like, this is Coburn Sound, just south of Fremantle, and a couple of satellite images here, just sort of showing you on the left a recent algal bloom brought about by sort of unseasonal weather conditions. And then on the right is a lot of turbidity from ships and shipping operations that you can see as they do their day-to-day work. But on the other hand, we also have a lot of endangered communities and highly valued ecosystem communities, including, for example, the pink snapper you can see in the top, dolphins, penguins, and so many other, really important values to the people of Perth. So the challenge has sort of always been, as it always is for environmental management, is how do we sort of juggle these competing uses? Essentially, they're all have overlapping footprints, they have overlapping needs for assessment. And when you're a regulator, whether you're like an EPA, for example, or a federal regulator, you want to be able to look at and build a holistic picture of all the things that are going on. But that's extremely difficult because it can range from some things that might just be a short-term impact, like a maintenance dredging program, or it could, refer to something that's much more longer term. Like for us, we have our desalination plant discharge going into the Sound, and that's sort of a multi-decadal sort of impact. So the question is really, how do we juggle all this? And the typical problem is that each one of these individual proponents will sort of prepare their study, and that study usually would have some data in it, maybe some modeling, and then that goes to the regulator, and the regulator is sort of stuck scratching their head a little bit, trying to synthesize the different time and space scales and the different potential impacts. So really the idea behind the underlying SEAF architecture, as sort of Chris introduced, was this idea that we could sort of collaborate and work together to come up with this sort of concept, what we call shared analytics. And that idea is that creates a streamlined set of rules for the players in that region. And it also gives a common holistic picture up to the decision makers and other community stakeholders. So what this looks like for Cockburn Sound. Now, obviously, like Brendan said, every region will have its own plan to integrate. So just to give you a bit of an idea of what's important in Cockburn Sound, really we have these sort of challenges around stormwater inputs, like things like wastewater discharge and industrial discharge. We have legacy groundwater, polluted groundwater coming in. We potentially have legacy sediment loads from historical pollution. We have operational impacts, like you just saw the shipping tracks, for example. We have dredging and coastal changes, infrastructure. And of course, we're also experiencing more recently things like marine heat waves and changes to patterns in extreme events. So all of this sort of builds the need and the sort of wish list for us is, well, wouldn't it be great if there was a system that could integrate all the bits of data and help us model and understand what cumulative impacts are going on? And wouldn't it be good if, that was on a scalable infrastructure that could be used for a whole raft of policy design, but also, for assessing individual projects. So just a little bit of background. I'll get sciencey for a little bit just to give you a bit of background about the modeling platform we use. Now, this again is specific to this Cockburn Sound. It's essentially a combination of oceanographic and weather models mixed with biogeochemistry models and ecosystem response models. And I'll go over a few of the components in a minute, but essentially we have a core model. But to make that model work, we need to connect it to a bunch of external drivers. And those external drivers in the modeling community, we call those the boundary conditions. And the boundary conditions for our coastal example are these 8 things that you can see here. And they range from what we call the environmental drivers on the left through to the sort of more industrial drivers on the right. So just to give you a visual of what that model might look like, here's an example of the prediction. You can see here the different hydrodynamic physical environment properties being predicted here by the model. And you can see, even if you look closely, you can see there's a wastewater discharge in the south. There's cooling water discharges over in the east and so on. So the model itself is built by a bunch of very complicated model data workflows. And I won't go through all the technical details of those, but just want you to sort of appreciate that just to run one comprehensive simulation, we need to glue together a whole series of different modeling and data tools. And so part of the motivation of the SEAF infrastructure was to sort of streamline how those models can sort of seamlessly interact, even if they're operating at different scales or operating across different disciplines. So if you look from left to right here, we're going from global scale predictions down to our local. And then as you go from the top of the page down, we're sort of integrating from, what we call the ocean type physical conditions up through biogeochemistry and into benthic and pelagic ecology. So the goal of the model, again, we're not trying to make one monolithic model that does everything. The idea, though, is that we build these sort of reusable, repurposable model data integration workflows that allows us to sort of connect these things together a bit like Lego. We can also have different resolutions of the same model, but for different purposes. So for example, we might need a dredging simulation by one of the proponents to run down to like meter resolution to look at dredge plume dispersion. But on the other hand, we might also want to look over longer timescales, like 10, 15 years. And so the idea is that we want to just be able to sort of change the spatial resolution without changing the underlying model fabric. Now, to drive a big complex model like I've described, we also need a very well-coordinated data set. And so to do that, we sort of work on the premise of data federation. So that is, we sort of go around and audit all the relevant data. And there's a large amount of data from, dozens of different agencies and different companies and local researchers. So we put all that together through this process of data auditing and cataloging, and then we create what we call these sort of ingestion pipelines, which take or connect to APIs, for example, harvest data. They take that data and they bring it into some sort of standard nomenclature and having standard metadata. That's then used to create sort of standardized and version controlled data products, which can then be used for either modeling or any other downstream purposes. So just to give you an example of what that looks like for Coburn Sound, I've just cherry-picked here one image from a water quality theme in the data catalog. And you can see here, these are all the measurements that have been identified over the region. And you can see all the different agencies that have participated in data collection over the last 20 years. And a lot of this data is actually in private hands. So it could, for example, be owned by the water utility, could be owned by companies, but some of it is also public data and in the public realm. And so the idea is we can sort of understand those different types of data. And in fact, most of the data, if you add it up by number, most of the data collection in this region where the assessments are happening is actually owned by companies. And they submit this data to the EPA when they're going for referral, but this data doesn't always make its way back into our models and our cumulative assessments. So that's one of the things that also motivates us to bring together. Here's another example where we can, just to make the point that we can bring together quite diverse data sets. So the yellow and the gray on the left there is a sensor on the bottom of a ferry to Rottnest Island. So that data is also able to be ingested into the framework, and that's useful for us to validate things like our temperature in our model, which is an important variable. Or the one on the right is research vessels leaving out of Fremantle to do their oceanographic cruises. So the idea is we can bring together very, very diverse data sets, but we harmonize them through this data federation approach. Again, won't go into the details, but just to highlight that we sort of bring in these data nodes. And a data node could be a static data set, like it could even be just an Excel spreadsheet, or it could be a link to a dynamic API where we're getting live data feeds, for example, from some sensors where there's telemetry access. And we bring that together through this ingestion pipeline to create these data products. And data products can be sorted by agency, They can be sorted by thematic category. They can be public, they can be private. And once we've got these data products, we can sort of use the power of the combined data set to sort of move forward with our assessment. So the first point to make once we've got all this data and model is that we really need this coordinated alignment between the data products, the environmental modeling tools, and also the cloud infrastructure. And together, that's what makes our integrated modeling system work. Now, I've shown you the model that we've described for this particular assessment, but you could imagine any other model being in here. It could be a groundwater model, it could be a machine learning model, it could be a biodiversity spatial model. They all could essentially fall into the same pattern. Now, the idea is that there's these sort of, once you've got these three pillars standardized, then we can use the modeling and the data for a bunch of different things. And that could be like regional planning assessments up in the top right. It could be for design scenarios. For example, if a company wants to sort of optimize how they're operating in the environment before submitting any sort of plans for the environmental regulator to approve. Could just be for things like looking at data dashboards to track what's going on. And increasingly, we're also interested in being able to do forecasts and projections seamlessly so that as things change, we can sort of have this sort of, we can sort of anticipate what's happening more than reacting to what's happening. So as an example, one of the challenges in Cockburn Sound is hypoxia. So this is where you get low oxygen in the bottom waters, and that's what you see here in the yellow and the red. And in the bottom waters, that sort of builds up. It really causes nutrients to release. It potentially leads to fish kills and things like that. So this is an example where we get the data from the data catalog and we use it to validate the models and understand what's going on. So this is like validating the model on an individual environmental event, but we can also look at, how alternate scenarios and different projects could potentially worsen this. So one particular concern in mind for this issue is we're talking about upgrading our desalination plant in Perth's coastal waters, which would include more brine going into the bottom waters and may lead to further stress on these sort of items. We're also interested in sort of going up the food chain to look at water quality aspects, so nutrient cycling, things like harmful algal blooms, which are becoming increasingly of concern. And I won't go into the details here, but just to say that we can sort of stack and connect these models. We don't need to always run these models in entirety. The idea is they're relatively flexible. So we say horses for courses. So if we're doing a dredging study, maybe we're focusing on turbidity and light. Whereas if we're looking at, wastewater management, we might be interested in the fate of nutrients and risk in algal blooms, for example. Okay, so coming back to the SEAF platform. So you know a little bit about the science now. You've seen this big horrendous data set. You've seen these complex models that we're trying to put together. Now, how do we make it all work from an analytics point of view? And the way we do it is we introduce this idea that Brendan described earlier, which is this concept of a landing zone. Essentially, we create a landing zone, and within that landing zone, you can have different users, and they can all be, vetted in terms of their user authentication, and wherever they're coming from can be, ensured. So that it's not necessarily a public zone. It could be, it would be quite a secure environment where the users can operate and do whatever analytics they need. In our case, for Cockburn Sound, we have our model configurations stored in the cloud, and they're all version controlled. And then we have all our data products archived on the PAWSI supercomputer in Western Australia, and we access that on demand. And so they can be pulled into any landing zone once it's instantiated, and then you can do whatever you want in that landing zone. We've got some custom or bespoke tools that allow us to run those models that I just showed you earlier. So when it comes to the concept of a landing zone, this is where it gets right down to the sort of DNA, the fabric of the SEAF facilities. So essentially, a landing zone could be configured in any number of ways, but it could be having like a private area where just an agency wants to do their own work, but they're using the standard tools and the standard architecture. But we can also have things like shared zones or collaboration zones or encrypted zones. And that's where maybe where there's highly sensitive decisions or highly sensitive data, we can get collaborators or even competitors to come together to work on an example. So the best case in point here is in Perth, we have the Water Corporation and the Westport, which is the Department of Transport in Western Australia. They both need to submit an environmental referral for the same region because they're both proposing to do projects in a similar region over a similar timeframe. So how do they do a joint environmental impact assessment even though they're separate projects? So they need to know about each other's potential changes, and they want to see what each other are doing when it comes to designing their modeling going forward for the purpose of cumulative assessment. So what does that look like in practice? Well, first, we have this thing called code as infrastructure, and essentially you can instantiate very simply a virtual private network, which allows you to operate a virtual organization, essentially, just like you would in your normal organization. You can have multiple computers, you can have multiple services running to allow you to run a fully fledged enterprise in the cloud. Then you choose your zone architecture, if you like, or you can create a zone to have whatever resources you want. In this case, for example, we have two areas. We have a more general area where we have data services. We have things like Databricks, and you can have virtual machines and whatever you need in that zone. And we've also got a special subnet where we work with a collaborator called Sentient Hubs to develop very custom workflows for some of the more complex Earth system modeling that we do. The third step is really then to bring data in, and that could be either public data in our public repositories that has been coordinated through the data auditing process, but it could also be links to private and secure data channels into your specific zone. Once you've got your data and your zone organized, you can then sort of do your modeling. I've shown you the example of the modeling we do in Coburn Sound, but it could be any other types of models that you could imagine. Once you've got your data and your models running, you can do whatever analytics you need. So that could be running, maybe you want to run virtual machines with Python scripts, or maybe you want to run GIS services, things like that. And then finally, you can also include other web services in a zone. For example, like we host dashboards, or you could have, AI services and things like that. So the other point to make is we've designed SEAF that a zone is really not the same for everyone. So we can use common data and common models, but we can have different purposes within a zone. So this will make sense in a minute, but essentially, as an academic in a university, I'm sort of interested in running a model in a certain way. But if I was a consultant working for a client, I want to run the same model, but with a different focus and a different use case in mind. And then finally, if I was a regulator and sitting in government and trying to work out the long-term policy, I want to run the same model again, but with a different time and space scale in mind. And then finally, there could even be operational decisions. For example, our water corporation here are worried about, what's going into the intakes of their desalination plants. So we've got all these different users and use cases, but they can all use the common infrastructure in a similar way. So just to give you a bit of an example of that, the main purpose of our work at the moment is to help support Westport and their consultants to undertake a dredging assessment. So it's one of the largest dredging programs in the region, and they want to be able to run many, many scenarios to explore how to best optimize their dredging program with least impact to the environment. And so you can see here we've developed this web tool where they can sort of within a zone log on, run the models, run scenarios, quick turnaround. These models would normally take, several days to run on a supercomputer. We can now access resources through the cloud and run many models in parallel and have them all version controlled and archived, ready for later inspection. Another example would be we could spin up a zone for a slightly different purpose. This is an example of where one of our marine ecologists was wanting to use some of the outputs of some of the modeling alongside some benthic camera data to come up with some habitat mapping type models as well. So totally different type of model, but again, using that common infrastructure to identify and where we can sort of identify best areas for restoration. More recently, we're talking about how we can use the same underlying fabric to support real-time decision-making. So this is a proposal we're putting together where we would look at coastal blooms in Perth. Many of you would have seen the news recently about some of the big blooms in South Australia. And so the issue is, can we use this same underlying architecture but in this sort of real-time operational mode? So just to finish up, basically the idea is you can still do the modeling and collate and work with the data as you wish for your particular use case. There's no requirements that you have to use a particular model or a particular way of doing things. The idea is, though, that we use a common, or we say common architecture, but a common fabric. And essentially what we've been able to do is show how we can sort of spin up these zones for different use cases. So this is a bit of a herendogram just showing some more specific things to the local project. But the idea is that as the model's been evolving in complexity, we're able to spin up and then share that model with industry. They do their assessment, and then that goes onwards and upwards for decision making. But what we're really trying to show at the moment, and where the challenge lies, is how do we've got all these different proponents doing models, coming up with designs and doing assessment. Well, one of the key aspects, what we're trying to do is make it so that then the regulator has the same common architecture. They can see in a very compatible way how these different things are being configured and how they're being run, to the point where the regulator can then sort of take what they've done and rerun it and put their own analysis over the top of it. So this is the idea for cumulative assessment. Essentially, projects and proponents can continue to do their secure design work in their own zone. And just to highlight that once you're in a zone, no one can see it, not even the designers of the model, not the regulator. So a zone is completely private. But only when they decide that a project is ready for referral will they be able to then send up their selected information up to this sort of collaborative zone, which is where the regulator sits. So hopefully that gives you a bit of a flavor of what we're trying to do. I know this is a bit of a technical slide, but essentially the idea is that we're moving towards this concept of shared analytics without sort of necessarily enforcing everyone uses the same model on the same computers with the same data. We have the same underlying principles and model components, and users are still free to innovate within a zone and compare different models and do whatever they need to do as they would normally. But the benefit of this is it creates this sort of repeatable and sustainable way of using the models and the data. It really, we use this term horses for courses. It can accommodate use cases for diverse use cases, really, using the same underlying infrastructure. So it's very quickly to onboard someone to get active with the data or the models, like just in a very short amount of time. It's tailorable to compute preferences. So many consultants, for example, might be happy to pay thousands of dollars for doing some projects in the cloud compute realm, whereas academics, for example, might like to link to national infrastructure for running cloud compute. And it also, one of its big advantages is that sort of, because it sits above institutional IT networks, it sort of sits above the traditional IT barriers that are amazingly complicated for individual organizations to work through when they're trying to develop new software capability in-house. So overall, the goal is really that we want to sort of, use this approach to foster synthesis by linking different stakeholders coming together to sort of lift the knowledge and the capability across the whole sector that is using that's active in a particular environmental region. So I think that's probably enough there, but we've got plenty of time for questions, and I'm sure Brendan and Chris will be happy to also talk a little bit more about some of the approaches to the SEAF program.